I hear you here.
Excellent. Okay, so I just like to I see a couple of Japanese names there, and so I would like to say "Osoyo gozaimasu" to you, which means good late evening to you. So I would like to thank Gregory for inviting me. I don't think that I'm necessarily the wisest person here, but I'm one of the oldest, and so if that makes me right, then I'll hope you will hear what I say. I would like to give a talk that is basically in two parts. In fact, these are the parts. The first half is about the whole panorama of solar physics as I understand it, and I'm going to illustrate that with a Quiet Sun movie. And then the second half is going to be what I think is the future of solar physics, and that I see largely to be in the chromosphere and at high energies. And that's also got a movie in it, movie number 2. And the format of this webinar series is something that I guess is exploratory, since this is the first example, but I'm very hopeful that it will continue, because at an opportunity to speak from people to people at all longitudes, pretty much, except for Hawaii, including Irkutsk and Glasgow and North America. This is a wonderful way to connect. And so the level of the presentation that I will give is obviously lightweight, because I have to start with the whole panorama of solar physics at Gregory's request. But it is at a level that includes novel ideas, I hope, and I'm very seriously interested in getting feedback. I think this format in the WebEx permits people to ask questions and to get them documented with answers in fairly short order. So I'm looking forward to that, and let us go ahead then. So please ask questions, I guess, with Gregory to moderate questions of clarity, clarification, or but not deeply significant, and so save the real questions until the end. Okay, so the panorama of solar physics is quite vast, as you know. We have a whole star to work with. There's very active research in all areas, all geographical areas, well, heliographical areas of this star. In the interior, it ranges from nuclear and particle physics, axions. I work on dynamo action, convection, the nature of the star as a star. And in the photosphere, of course, going up now from the interior to the exterior, the panorama continues to the photosphere, where we see sunspots forming, signatures of convection, but the sunspots are clues to magnetism. The chromosphere, oops, already I've gone on to the next slide. I didn't want to do that. Let me go back to my panorama slide. No. Yes, okay. The chromosphere is where everything changes, and I'll talk quite a bit about that as we go along. Changes in the sense of the medium stops being collisional, but let's get to that later. The corona, of course, is the extended atmosphere of the sun, and it contains a lot of plasma physics, and is a very complicated and interesting place. And again, there's plenty of new research that's going on in that area. And in the heliosphere, there's just an amazing amount of body of work which I'm not as familiar with as I should be, about, for instance, planetary magnetospheres and the interactions of these plasma bodies with the solar wind and the heliopause, and the place of the global solar atmosphere in the interstellar medium. Okay, so the panorama is vast, and it's very active in all of these areas, and it's blessed with many, many nice instruments in space and on the ground that are doing wonderful new observations. So this is a Dave Hathaway special. You've all seen this, I think. This is just showing synoptic maps over 40 years of the coming and going of the sunspots cycle as seen in line of sight magnetic field obtained from space, from SOHO, and from, I guess, from SDO as well, because the end date of this movie is 2013. And you can see the solar cycle. You can see the Hale progression and the reversals of polarity, maximum and minimum. And here we are coming up now at the present time in 2018 on solar cycle 25. So if you're familiar with the RESI Science Nuggets, you will find the most recent entry there is on the first sunspots of solar cycle 25 and a flare. So already solar cycle 25, in some sense, has started. And that particular RESI Science Nugget, which was written by Tomasz Mroczek of Wrocław in Poland, has already got a couple thousand hits in its first week online. So people are really interested in the long-term development of the sun as reflected by the solar cycle. Okay, so why do we study the sun in general? As a star, it's only one of many, and so it's not so uniquely interesting by itself, but it's nearby, and we're grateful for that. As a plasma physics laboratory, it has many interesting features. We can resolve it, and we can resolve it spatially and temporally and spectrally in many ways, but not completely yet. We still have many observational domains of parameter space that we have not covered on the sun. So there's plenty of future interesting science to do in these domains, but we are getting at them better and better. And I'd like to interpret these things as messengers. This is a buzzword that's very interesting now because of the recent discovery of gravitational waves from colliding black holes. Exclaimed people, this is multi-messenger research, astronomy. We can see neutrinos and all kinds of strange things coming from this black hole coalescence. Well, we get multi-messenger messages from the sun in many ways as well. And so this is one of the things I'd like to point out. Our field is a multi-messenger interdisciplinary field, and all of these parts of the panorama really do play together in some way, shape, or form. So to continue this, I've said that, but there are a couple of quotes here that are famous. One is from Bob Layton in red there. If it weren't for its magnetic field, the sun would be as boring as people think it is. True fact. Number two, from Van de Hulst, magnetism is to astrophysics as sex is to psychoanalysis. It explains everything that we don't understand. So that's in a sense true, but magnetism, I don't think, is the correct way to describe it. So I put that red question mark in there, and I will come back to that point as we go along. In terms of relevance, solar physics is, because of its unique position, the sun gives us information about what we call space weather now, mainly the impact on Earth and humans' systems around the Earth. Everybody knows about that. There are also paradigms for magnetic activity. We see the activity, and we see it on many, many stars. The wonderful Kepler observations, Maehara et al., for example, of stellar flares, are examples of that. And so what paradigms do we apply to understanding the physics in these more remote objects? Well, we look to the sun initially, and we look perhaps to the cartoon archive, and we try to learn how to tweak cartoons to explain any unique features that we see in the non-solar application of these things. One of the main applications that people are really interested in is astrobiology, because of the influence of stellar activity on the possible influence of stellar activity on the development of life on exoplanets that are Earth-like. So that's a large development of research there, a lot of it quite flaky, a lot of it heavily dependent upon our understanding of how the sun works. And for example, one aspect of that is the concept of the stellar CME. We see CMEs on the sun, and their particle radiation is probably more important from the astrobiology point of view than is the ultraviolet emission and the X-ray emission from the stellar activity, which is more direct. But the particles are a colossally important aspect of stellar activity. And these particles on stellar SEPs are very hard for us to assess observationally. We can do what we can do on the sun and try to extrapolate that information. And in high energy astrophysics, this is a fourth bullet here on relevance. High energy astrophysics, all the features of high energy astrophysics are present on the sun in a microscopic scale, except for, of course, a black hole. We can detect neutrinos, neutrons. And these are advantages that we have over high energy astrophysics observational work in other areas because the sun is so close. The solar cosmic rays are just like galactic cosmic rays, except they're not so, the sun is not so powerful as a supernova. So, but all the same shock acceleration mechanisms are there, for example, for us to work with. Historically, solar physics actually at first began with the photosphere, with presumably Galileo and Scheiner, and who's our English hero, people who in the ancient Chinese records of visible light sunspots. The sunspots and the photosphere were what people could work with in the mid-1800s because of optics and telescopes being available. But even at that moment, in the mid-19th century, the first glimmers of space weather could be noticed because people had geomagnetic records on the Earth of very great sensitivity. This is based upon the observational side of Gauss, actually the famous mathematician Gauss, who invented the Gauss variometer, which allowed people to make very precise measurements of the terrestrial magnetic field, which is intimately linked to the solar wind and to disturbances on the sun, which were eagerly being explored in the 19th century. At the end of the 19th century, spectroscopy had gotten to the point where one could detect the chromosphere spectroscopically, H alpha in other words, and so in the early 1900s, this was the big thing about solar physics. One could deal with the chromosphere, one saw flares. There were, I think, 5 recorded solar flares in the 19th century, but as soon as one could look at H alpha and see the chromosphere, there were many, many more. And now, of course, we have radio wavelengths. So the radio and satellite observations in the late 20th century and to the present, we have the corona as a fantastically beautiful and well-observed large-scale structure, mostly optically thin, so we can see it, and doing all kinds of deep things. So that's the modern era. But I think actually we're on our way back to the chromosphere in terms of the cutting edge of research. And I'll explain that a little bit further. The chromosphere is such an important place, or by chromosphere I mean the domain between the photosphere and the corona. So I think I have a graphic here. Yes, this is the photosphere corona interface region. The red circle is meant to be the chromosphere, and the black circle is meant to be the photosphere. And here's a list of half a dozen things that happen in that red zone. One thing is that there is ion neutral physics. In other words, it's not plasma physics of a fully ionized medium. It is not a fluid, hydrodynamical fluid. It is a place where there is interaction between ions and neutral particles. And that, of course, is a strong function of height and all kinds of parameters, but it's happening all in that red zone. In that red zone also, one sees a big jump in the plasma beta. Of course, the interior of the sun is more like hydrodynamical, and the exterior of the sun is more like magnetic, and so beta crosses unity in that red zone. That corresponds to the loss of collisionality. If you go into the corona, you find that particles can propagate freely, scatter free, you would call it. And of course, the major thing about the black circle there is the end of optical depth for photons, right? The photons become detached. No longer is there what we call local thermodynamic equilibrium. As one goes out from the sun, in the interior, radiation carries the energy. At the surface of the sun, that stops. Sorry, I phrased that incorrectly. Let us just say that the optical depth vanishes, and so the radiation is not coupled so directly to the chromospheric plasma nor to the coronal plasma. There's a big temperature jump, which many people think is a mystery, but I'm a fan of Jack Scudder. I think that it's not a big mystery. I think it's a natural consequence of the way these things happen in this red layer, which is also another point here. Let's see. this kind of out of order convection threshold. Well, that's part of the energy transport I was trying to mention. And then the main thing that we love, that I've always worked on personally, is flares and transients. These things happen in the corona, but really in the chromosphere as well, and importantly. And so this is something, a characteristic feature of the nature of this interaction between the interior of the sun and its exterior, namely that there is this punctuated, sporadic, spasmodic buildup of energy and its sudden release as a flare or some other kind of transient, such as a coronal mass ejection. Now, the interesting thing about all of this is that it is in this red zone, the interface layer, where all of these strange things are happening, which are very complicated physically and very ill understood in many ways at the present time. But inexplicably, this is often where you put your boundary conditions. You put the boundary condition for coronal MHD modeling often in the photosphere without the benefit of a chromosphere. Is that legitimate, given all this physics that's happening in the chromosphere? A good question. Likewise, for the interior of the sun, if one is dealing with helioseismology, from which we can learn about the interior, what is the outer boundary condition for the modeling of the frequencies that are measured so precisely? It's put right here in this black and red domain where the reflection of the sound waves happens, and so that means that the boundary condition is in the place where all of the physics is. And so I find this to be very disheartening in some sense, because the credibility really, I think, would depend on having the interesting physics contained within the space that one is analyzing. Okay, and here's that space. This is Sven Wedemeyer's take on a cartoon description of this interaction zone. It's horrible. It's just fantastically complicated. I don't know if you can all read this, but there's a fluctosphere in there, shock waves, current sheets, canopies, all kinds of stuff. And through the magic of PowerPoint, I have taken his cartoon and compressed it. At the bottom there, you see something that's kind of more along the lines of the actual aspect ratio of horizontal and vertical scales. And you can see that what looks like complicated curved field lines in the corona collapse, or heading towards the corona, collapsed down and become horizontal. So this is a major comment about the nature of magnetism in this interesting interface zone. There has to be a strong horizontal field simply because the field has to balance plus and minus, and it has to do so locally within this domain, a lot of it. Okay, and I'll come back to that in the context of gamma rays in the second part of this talk. How am I doing for time? This is pretty much on the schedule. Very good. Okay, so multi-wavelength, multi-messenger astrophysics. I'd like to say that in solar physics we have a, what do I actually say there? I say we have broadly available data of all kinds, and we often use it as opposed to other fields of research in which people may narrowly try to exploit, one particular kind of thing or another. In physics, you can focus in on the laboratory and make a precise measurement of a specific thing. In the case of an astronomical object, we always have multiple messengers, and the better we use them, the better off we are. And in solar physics, we're accustomed to quite a public exposure of all of the data, and that's good. So I'm just noticing, and I'll call to your attention one very interesting paper that I just spotted on arXiv from Yegorova et al. 2018. I'm not going to comment on the correctness of this paper because I haven't really read it carefully yet, but it represents an amazing mixture of things ranging from galactic cosmic rays, global warming, that's our space weather business, space climate business, variation of the total solar irradiance, and solar millimeter wave astronomy with ALMA. This is all bound up in the work that they have done in the area of trying to characterize the Maunder minimum. You can see in the plot there that dip at 1700 is meant to represent the forcing function, the global energy input from the sun, as characterized through this concatenation of different things across the timescape there of 2 or 3 centuries. And so this is, if it's true, this is, I think, sort of a direct confirmation of what Jack Eddy said, that by golly, yes, the Maunder minimum did to crank down the solar radiation, and yes, you could see canals in the Netherlands freezing and people starving to death in Europe because of the mini ice age. But you can also see that by and large, the steady input of heat from the sun has not changed. I think that's the interpretation that they would give. But I would just call this paper to your attention as a good example of multi-messenger astrophysics in the solar context. Okay, there's a caveat to that. Despite all the stuff, all this information that we have, sometimes people do research in the solar area that is too focused and too parochial and does not take into account, for instance, the implications of a cartoon. They will take a cartoon and just try to flesh it out in terms of their particular observational results. Typically, people don't pay enough attention to the big picture, so that's my humble criticism. Okay, so that ends part 1 of this presentation. I'll just say multi-messenger because I like that term, and I will say that I think that the future developments in solar physics, although there's this broad panorama in which there's powerful progress in all areas, I think the future that's really interesting for me is the imaging spectroscopy of this transition layer, which IRIS is a good example of in space, in the ultraviolet, and DKIST will be an excellent example in the visible ultraviolet range and infrared from ground-based observations. So I think these areas benefit a lot from the technology that we have gained, and specifically in data acquisition and processing, because large volumes of data are involved. So I think that's the future, basically. But also, I would say that high-energy astrophysics is an important thing, and I will be talking about that in the second part of this talk. An omission from our current understanding, what is that? Birkeland currents. So here's a picture of a dusty volcano. This is not on a star, this is just on the Earth, and you can see all that flickering lightning going on. It's amazing. And so it has nothing to do with the sun, but just reminds us that in a structure in which there is some sort of dynamo action, in this case it's dusty plasmas that store up static electricity, you will have currents flowing. Okay, and so this was something that Birkeland noted in the terrestrial context, and this cartoon of 1908 there is going to be in my archive on its next iteration, and it shows cathode rays streaming around the Earth, reflecting in a current system. You see the horizontal arrow there, which is in the ionosphere. And a modern version of that on the right is my old friend McFerron's cartoon from 1972 that shows the current kind of thinking about the way these Birkeland currents close between the ionosphere and the...
I cannot find out in the plot what does EMF stand for.
Electromagnetic field.
Okay.
Sorry, electromagnetic force.
Okay.
So this is the voltage, right? This is the important thing. A Birkeland current is a direct current, a field-aligned direct current, and a non-neutralized current in solar jargon, and it has to be driven by a voltage, and the voltage is EMF. This is just the term we use. So the voltage, a DC voltage has to exist to drive such a current, and it's carried by particles, of course, and not by a fluid. So that's easy enough to understand in the terrestrial case, because there's a very large EMF of a V cross B convective electric field across the geotail in a planetary magnetosphere. And this very large, hundreds of kilovolts, this large potential is there to be merged into geoelectricity and to cause these currents to flow that are called Birkeland currents. In the case of the sun, it's not so simple because there is no solar wind, or actually there is, but it's not blowing past the sun. There is instead the curl of B in the interior of the sun. So I think a good description of how the Birkeland currents in the solar corona flow is as a result of this mapping of this curl of B into a weak electrical potential structure. And you can do this on the back of an envelope. You can calculate the voltage that's necessary to drive the currents that are inferred in the corona. They've been measured since Crimea. Who's our hero in Crimea? Severny actually dared first to use Ampere's law to learn what the vertical currents were in the solar atmosphere, and we know what they are much more precisely now. It's pretty much scale invariant. We can do that Amperian integration and get the current, the total current, and we can use Spitzer conductivity to infer a voltage, and it is a few volts. So this is enough to drive the non-neutralized coronal Birkeland currents that are present everywhere, especially in active regions. And I'd like to advertise this book that's just appearing, edited by Andreas Keiling et al., Electrical Currents in Geospace and Beyond. Our moderator, Gregory Fleischman here, has got an article there, and there's articles by Georgolis and by others on the solar electric currents, but they don't really use this term Birkeland current, nor do they actually talk much about voltages, except in the case of the article by Don Melrose, where flares are mentioned. And of course, in a flare, it's not a static situation. It's not a DC current. It's an impulsive current. And so the EMF, the voltages that appear, can be enormously different, much, much larger, gigavolts. And so that's discussed in this Melrose article. And I recommend the articles in this book because I think it's appearing just at the right time to inspire the future research in this area. Okay, so I guess that's the end of part one. And here we are at 7:30. So, okay, part two, and now it's going to take off from this, and I will give you some comments about high energy astrophysics and how it relates to these things. I'd just like to point out that in this domain above the transition zone, typically it's non-thermal. Typically it's not LTE. Typically there are populations of particles that are present at many, many KT. KT in the photosphere is like an electron volt. In the corona we have a tenth of a kilovolt, all right? But when there's a dynamical process, we've got thousands of KT, and we have got large numbers of particles at these very high energies. There's a very nice analysis that was done by Dick Maywalt and his colleagues at Caltech, who note that the ultimate dissipation of the CME-driven shock wave in the heliosphere, the ultimate dissipation, a large factor of it, 10% perhaps, or who knows, is actually in MEV protons, the SEPs. And so the ultimate dissipation of that large amount of energy, which is associated with the flare sometimes and sometimes not, is actually non-thermal. And in that sense, we have to, I think, from a starting point of view, think of the corona as something which is not a fluid, but which has particle populations. And I'll just, an extreme example of that, of course, is that if you go out into interstellar space, far from stars, but still in the galaxy, and just add up the energy content of the stuff you find there per unit volume, you will find that the cosmic rays are much more energetically significant than the starlight. And so at some level, stars, and I know this is kind of cheating because they include supernovae, actually their main function is to produce non-thermal particles, not light. Okay, so now the reason for me being interested in this now and talking to you about it is that Fermi has produced some wonderful new results. And before I get into them, I'll show you this flare movie because it's one of my favorites. It's from Trace. flare of 2001, April 15th, and you can see all kinds of things happening. And the magnetic field is clearly participating in the sense of implosion and dimming and loop formation. And watch these jiggles here. You see the coupled oscillations of those loops. This is coronal seismology at work. There's the dimming. Okay, so you've seen this kind of movie many times before, but it's just pointing out to you that it's so rich. Okay, and so now, how do we relate that to gamma ray astronomy? This is what the sun looks like to Fermi LAT, the Large Area Telescope in Fermi, which observes above 20 MeV up to GeV particle photons, very high energy gamma rays, a zillion times KT in that sense. On the left, there's the sun. On the right, there's a blank field, equivalent blank field. If you do the analysis, which these people are very good at, and measure the brightness of the sky as a function of elongation away from the center of the sun, that's on this plot. And it turns out that there are two components. There's one component which is they call the disk emission. That's the red error bars there. And there's another component called the IC emission. That's the green zone, the dashed line towards the bottom. IC is inverse Compton. So the disk emission is gamma rays that come from primary cosmic rays producing secondaries that make the sun relatively bright. And the IC emission is Compton scattering by cosmic ray electrons. Again, relativistic cosmic ray electrons scattering on visible starlight, sunlight in this case, and producing this very broad feature. You can see the elongation angle of this component is still at the 10% level out to 5 degrees. So this is a corona. It's a large halo of weak emission that's due explicitly to, and this interpretation is makes good sense, explicitly due to cosmic ray electrons. So now, with both of these components, we have a way of seeing cosmic rays interacting at the sun, and this opens a new territory in our understanding of the solar atmosphere. So I've said these things already. Actually, there is a recent arXiv paper on something new from arXiv, which I'm not describing here because it's hard to understand. There's a paper by Linden et al. That describes a third component at very high energies, which is spatially resolved around the periphery of the sun in a very strange way. So I would recommend somebody to study that and explain it to me. Okay, so related to this, there is the concept of the cosmic ray shadow. I don't know if all of us are familiar with this. This is another high energy thing, not gamma rays. This is primary cosmic rays at TeV energies as observed via air showers. Air showers being observed by these large arrays, such as the ones in Tibet and in South America, the Auger array, and by HAWK in Mexico. This is a new paper by Aminomori et al. 2018. I love that name. The two panels show cosmic ray shadows. These are images of the sun seen in particle radiation, in cosmic rays at these TeV energies. And you can see the two panels are asymmetrically different. And that is because these cosmic rays are charged particles and they're being deflected by the coronal magnetic field. And it is responding to the sector structure in the heliosphere. The difference here is the result of the cosmic rays going to the left or going to the right, depending on whether the field is oriented in one direction or another. And so this is a powerful tool for studying a zone of coronal magnetic field, which otherwise you would not be able to do. This is basically seeing the field at the source surface and measuring it in a statistical sense over a long integration time. These maps probably took a year to integrate up to, perhaps more, but one gets fairly high time resolution, and it's getting better and better as the arrays improve. And the best of them is HAWK, they say, the best in terms of angular resolution and sensitivity. And I mention this because our friend Brian Dennis, if people don't know this about Brian Dennis, he just wrote a solar physics memoir, and he describes his early life in research in just this field of research, Cherenkov counting in large volumes of clean water in the Haverhaw Park array. So I recommend Brian's memoir. It's quite interesting. So I've commented on the solar shadow. It's different from the lunar shadow. There's a similar lunar shadow, which is just absorbing. The solar shadow has this lensing effect, or not exactly lensing, but this deviation of the cosmic ray tracks by the Lorentz force. Okay, so the reason I'm interested in this now is because this encourages these things encourage us to think about the limb shower development. So what I call limb showers is kind of a new thing, but not really, as I'll describe. It is the let me just leap ahead. The development of an extensive air shower. This is what people see with these arrays in Tibet and Auger and Hawk. Primary cosmic ray comes into the top of the Earth's atmosphere, for example, and it makes secondary particles. You can see all those blue things. Those are pi zero decay, gamma ray, direct gamma ray emission, pi mu e, Bremsstrahlung gamma ray emission, and a shower of these things very greatly multiplies the number. So one cosmic ray can produce tens of thousands or hundreds of thousands of photons across a very flat spectrum. Okay, and so how bright is that limb shower? Well, the limb shower is the air showers that are formed by a cosmic ray that is just coming in tangentially to the surface of the object. And the objects that are interesting here are objects that have extended atmospheres. These are in the inner heliosphere. These are the Sun, Venus, and the Earth. And in the outer heliosphere, there's Jupiter and any outer planet. These have these will have bright limb showers, very strong limb brightening as a consequence of this extensive air shower development. And the figure of merit for these I've calculated here. The Sun is the brightest of them, the most intense. That's because it's large. It has a pretty big scale height, and there is a substantial solar modulation, and you have to divide by the distance squared. So Venus is also a candidate. And the Earth, of course, is definitely a candidate because people have already seen the limb shower development on the Earth. It was predicted and described, well, not actually predicted, it was described in these very nice papers by Seckel et al. In 1991 and 1992 in terms of the diffusive transport and mirroring interaction of high energy particles in the solar atmosphere. So you can see on the left there a cartoon that Seckel et al. Used to describe the mirroring action. There's a primary cosmic ray that comes in and goes out through a flux tube. So there's a spatial scale associated with flux tubes that corresponds to a certain particle rigidity and a kind of a screening for this effect. The 92 paper points out that in this mirroring motion, which is really not very well described with their arrow, actually it is a helical motion, right? As the particle spirals in and hovers for a while at its mirror point and then spirals back out. As it goes through that mirror point, it can make a shower at any given point. The interaction length for a high energy cosmic ray is like 80 grams, something like that per square centimeter. So anywhere in that domain, which is in the deep photosphere, you will be able to produce this air shower, limb shower aftermath. And that's what's observed. First of all, the real theory started with Floyd Stecker. There's a 1974 paper where he did predict extreme limb brightening. You can see his little graph there. This was fleshed out in great detail in a paper by Morris in 1984 to prepare for the GRO Egret instrument, which was the predecessor of the Fermi and Lat instrument. These things will go very slowly, right? This is 20 years or 30 years between facilities. In any case, that work was done then. And now, with Fermi-Lat, one can make these maps. This was done early on in the Fermi-Lat observational program, and there is very much more data available now. You can see it as a function of energy. The inferred maps here focus down towards this extreme limb brightening that Stecker predicted. This is what I call the limb shower development. And this is how it works. As I've said, there's an isotropic cosmic ray sky. Isotropic, why is it isotropic? It is isotropic because people think that the propagation of the particles is diffusive on certain scales. So
For you, it's about 5 minutes left.
okay, this is about right. So diffusive screen of illumination, object with an extended atmosphere, and an observer sees the shower of photons. And the nice thing about this, one nice thing about this, is that there is no radiative transfer necessary. It's just if you any ray from any point on the screen can get into this observer if it needs to. Okay, so the implications of this are extreme, I think, not very well worked out. These are the first generation. It's a question of numerical simulation to understand what's going on, but that numerical simulation is very, very model dependent in the case of the sun, for example, because of the magnetic field. So that last bullet there that's in boldface, Seckel et al. Pointed this out, and they made plausible assumptions about the nature of this interaction, and they got within a factor of 10 of what LAT actually sees, which is very good. But the calculation depends very sensitively upon the structure that in this Wedemeyer cartoon, for example, and the sketch that they drew, the distribution of the magnetic field in the photosphere, and so in the chromosphere. So this is for us solar astronomers, solar physicists, this is a real bonus because this is a messenger containing information about a very unknown characteristic of the, and a very important characteristic of the interface zone, which is the magnetic field, the behavior of the magnetic field. So I'm looking very much forward to future exploitation of this tool. Now the flares also do this, and as you are all familiar, GLE number, ground level events number 72 in recorded human history, cosmic rays at the surface of the Earth coming from the sun for the 72nd time officially, occurred on September 10th of last year, 2017. And these red points here are the LAT observations. Where do these come from? Okay, so it's a strong tendency is to associate these with the SCPs because you can see at the bottom panel there, they are present, right? Although they are extended in time relative to this gamma ray signature, there are similar particle energies that can produce the gamma rays. And so a map in a paper just published by Omode et al. On this event localizes the sources, and you can see the red localization there in the first instance of this gamma ray event. At later times, yellow and green circles hours later. Still, all are consistent with the very extreme limb, and it's on a scale which is actually comparable to the, I mean, it's almost distinguishable. It is distinguishable from the corona as seen by Resi here. So the appearance is that Seckel was right, that the SCP particles actually get back to the sun, mirror there, and radiate in air shower secondaries. And so I've described this in a paper, which I won't go into in great detail, calling it the lasso model. My time is coming to an end. There's a classical cartoon by Kleiber, which I modify by pointing to the fact that the particle acceleration has to happen on closed field lines. They may be open as well, but on the closed field lines, the particles are trapped and they can be brought back to the sun, and they can do this mirror geometry and secondary particle production in this annulus. So I'd conclude with that, just to say that the chromosphere, I haven't talked about imaging spectroscopy in terms of the magnesium-2, carbon-4, iron-21 lines, all these things that Iris sees so well, but that's very important, and it will get more interesting when DKIST is available. But at the same time, I think we have to encourage people doing high-energy astrophysics and radio astronomy to study the solar atmosphere in a multi-messenger kind of way to put this all together. And I'd like to, just this limb shower business is what I'm working on now, so I mentioned that. So thank you very much.
Thank you very much. That was really very interesting talk. I now want to ask if there is any question or comment from people who are attending the meeting? You may either try to send me a note in the chat or try to unmute your microphone and ask question. And meanwhile, I want to ask, okay, so Dale Gary has a question. So Dale, please go ahead and unmute your microphone and ask.
Hi, you. Interesting talk. I'm interested in that, you know, the LAT results, the location early in the event. It seems too close to the flare site to jive with your lasso model, which seems to suggest that somewhere else this flux rope is coming down to the surface. Why is it coming so close to the, you know, the central part of the flare?
Well, it's my view. Well, the reason for that, I think, is that the shock acceleration is taking place at low altitudes on closed field lines. People talk about these as bow shocks driven by the CME, which is seen pretty much propagating in open fields. But I think that the shock disturbance begins at the site of the flare, and so closed fields close to the surface, where close would range from tens of thousands of kilometers out to a few solar radii, allows particles to be there near the flare site. It's a characteristic of all of the LAT localizations that the sources are close to the active region. But on the other hand, this is the fourth occulted event that they've seen where the flare is definitely behind the limb, and yet you see emission from the surface of the sun. So that implies some spatial distinction between the active region fields and where the particles appear. But I think it's close by. Does that help?
Dale?
Yeah, I just can you go back to that slide that shows the OMIDI or whatever it is,
yeah,
sources?
Let me try to do that. Are you seeing this?
Yeah.
Okay.
So the first circle is at 1557 to 1607. Yeah, the problem is the flux rope is so far away, so far out there already. It just seems difficult for me to understand how those particles anywhere near the flux rope are coming back so close to the flare.
Well, if you believe the shock acceleration ideas, the flux rope has nothing to do with it. It's a MHD wave, right? A large scale MHD wave, fast-mode shock. Maybe it's quasi-perp at the flanks of the structure, but it has nothing to do with the helical fields that you might see in a flux rope.
Well, I'd like to implicate the downward reconnection jet for this, actually, rather than any kind of shock wave moving outward like a blast wave or whatever you're referring to. So just a point that.
Yeah. Okay. Well, write a paper and I'll be the referee.
That should it be direct shock or might be reverse shock?
Oh, it could be well, to answer Dale's comment first, yeah, it certainly could be a shock, the stationary shock coming from the reconnection outflow. And your comment, Gregory, about the reverse shock is there's a paper by Kahn and who's our Finnish friend on that very thing, right? The shock, the reverse shock could also do the particle. Give particles access to the lower atmosphere more readily. But I think all of this is quite uncertain from a modeling point of view. People just don't know. And of course, the going in position that Seckel et al. Took was that the particle propagation is diffusive. Well, I don't think that's correct at all. I think the particles are quite directed, and they are on these scales. They have deterministic orbits that you can describe with the adiabatic invariance. It's just that you don't know the magnetic field structure, and it's changing with time. which incorporates all of this business about the electrostatic potential that you have to worry about. So I think that we're nowhere close to a beginning to understanding the theory involved with the relationship between these particles and these gamma rays. And that's why I dared to propose the cartoon with the tiger, because it's just there's nothing out there at the present time until Dale writes his paper.
Okay, while I'm waiting for requests for other questions in chat, I meant to ask you a question about chromosphere. What do you see, sort of what combination of data and modeling are needed to break through, to achieve breakthrough in this?
I think what people are doing, which is very difficult with Bifrost and things like that, is the right way to go. And I'm always asking them why they don't do two fluids. And the answer is we're getting to it, and they are getting to it. So I think the two fluid modeling is a very important aspect of this, because that allows you to treat the electrons and the ions distinctly, and that allows for electric fields to happen in ways that they wouldn't have happened in a single fluid. So the electrical potential, which I think the voltage, which I think is the essential description of these Birkeland currents, I think that will be much better understood once this kind of modeling happens.
Okay, thank you. Last call for questions. If there is no question, let me thank first all the participants for joining us. As I announced, we will put recording online, and you and others will have option to watch it and to send further questions or comments to me, and I will connect with you roughly in a week, record an amendment, and we'll put online.
Yeah, I'd like very much to endorse that. I think questions should be asked, and so I don't know who was participating this time, but I did see quite a few names. I think that all of them should feel free to ask questions. It's good to have the dialogue.
So it means if there is no questions right away, let me thank our speaker today, and I will announce further events later on. Thank you very much, and goodbye. Thank you, Hugh.
Thank you.
Thanks, Phil.
Thank you. Goodbye.